Hi, dear MECH 202 students. This video record is about the fundamentals of metal forming. Well, let us follow the presentation scrolling the slides. Okay. Metal forming. Yeah, it is one of the commonly used manufacturing processes. It is for shaping and sizing the material for having the product in the end. In the name you see it is written metal. This means material is a metal, not plastic, not wood, not any other, but it is metal. And here forming, saying forming, we mean set the shape and the size of the object. How? Not via cutting the material. Just via plastically deforming the material, permanently change its shape and its size. Well, plastically deform the material of the object, and then have the product as it is required by the customer or as it is decided fixed by the designer of the product. To be able to understand how the material is deformed and have the object as it is required in the final form, and of course to be able to solve some design problems or just reverse engineering to check whether the object it has already been manufactured can be used under the action of a different loading. Yes, it is necessary to make a review on the intermolecular forces, internal forces, within the object at any point, at any cross section. The internal forces are studied not only under such a title, metal forming in say manufacturing technologies course, but for the first time, yes, it is subjected internal forces, atomic bonding forces are studied in the content of Introduction to Mechanical Engineering course. But deeply studied in other course, it is common name is Mechanics of Material or Strength of Material. In MECH NCC curriculum, Mechanical Engineering curriculum, the introduction course, is it is called is MECH 100. The course it is about mechanics of material, mechanical properties of material, and also the mechanics of material. It is called as 206, MECH 206. Okay, following part of my presentation can find the slides. I selected those from the content of MECH 100. It is to make a review on the basic things, fundamental things. It is about the mechanical properties of material. Okay then. What is that? It is the isolated part of the universe. Using the definitions the same definitions. These are common definitions in thermodynamics. Well, the isolated part of the universe is called system. The rest of the universe is called surroundings. Well, in this illustration, let me take a pencil using this tool. Okay, this is our object. In the jargon that is used commonly in thermodynamics, it is the system. Well, the rest of the universe is the surroundings of the system. Between the surroundings and the system, yes, we have an interaction. Surroundings, thanks to the existence of some tools, well, can apply forces onto the system. For instance, well, imagine that there is a tool, okay, and using that tool, the element of surroundings applies such a force system. Well, if the contact surface between the tool of the surroundings and the surface of the system is in the comparable order relative to the total size of the object of the system, then say that load is a distributed load. It is a surface force system, and say it is distributed over the contact surface. But if the area of the contact surface between the tool of the surroundings and the surface of the system is like this, relative to the total surface area of the system is very small, then well, we use this idealization, say that since the area is very small, the force is applied at a point, this little area, like a point, like a dot. So we'll say that it is a concentrated force, or it is also called point force. If the contact area between the tool of the surroundings and the system is such a slender area, then instead of expressing the loading as per unit of the contact area, we express the load per unit of length. It is like a line, so per unit of length, the load function is given per unit of length. If the force system is the one, well, all the particles of the system just loaded by forces, all the atoms, all the molecules, all the particles of the system are under the action of the loading, then such a load is called body load, body force. Well, the most common body force system is the force system applied by the earth onto the objects. Well, the resultant of such a body force system is called weight of the object. And after finding the resultant of such a distributed load, say that it is applied, resultant is applied as if at such a specific point. That point is called center of gravity. Center of gravity point, you know. And well, from Newton's universal gravity law, starting from the expression, indent can find this compact form. Weight of the object is equal to mass. Mass is the proportionality constant between the net force acting onto the body and its acceleration, you know, times the gravitational acceleration. Everybody knows that it is the formula to calculate the weight of the object. Okay, well, in statics, In dynamics, well, mainly, the external forces are subjected. But in, mechanics of materials, strength of materials, design courses, and also under this title, what metal forming in MECH 202. Well, not the external forces only, but we mainly study on the internal forces, atomic bonding forces. Okay, if the externally applied loads are those, then for instance at this cross section, imaginarily cut the body and then, well, answer the question at this cross section, which forces are to have to balance the effect of the external loads. Of course, the answer just the atomic bonding forces. Okay, then, for instance, do it. Yeah, well, it has been isolated. You see. Well, the other part, assume that has been removed away. Well, the externally applied loads are balanced by the atomic bonding forces. At the cross section, we have the forces applied by the rest of the body onto the other. At the cross section, we have practically infinite number of bonding forces. What is that? This is the resultant of the atomic bonding forces. Well, it is a common practice, well-known thing. Well, that force is resolved into its normally directed component. This is the normally directed component. Well, say that F sub n is the normal component, and the other component is the tangential component. This is, say that F sub t. Although here it has been denoted with capital V, it is misleading. Say that force component of the resultant of the atomic bonding forces in the normal direction, component in the tangential direction. Well, this component is called normal force. The tangential component is called tangential component, tangential shear force. Tangential component is called shear force. Okay. How about the turning effects of the atomic bonding forces? The resultant turning effect is here, resultant moment. It is normal component is called torsional moment. It is tangential component is called bending moment. Okay. Well, these are the atomic bonding forces. Their also turning effects moments. But in studying on the strength of material, rather than using the atomic bonding forces, we use atomic bonding forces per unit of the area of the selected surface. Well, that is the selected surface, selected cross section, and then, well, find the area of this surface and then say that normal force F sub n divided by the area of the surface. You're looking for or studying on the atomic bonding forces at which cross section, then, well, use the area of that cross section of that surface and write this expression: normal component divided by the area of the surface. This ratio is called in general stress. If the force is the normal component, then the stress is denoted by the capital S in Greek alphabet. It is this letter, and in reading say sigma. Okay, by definition, stress, it is the normal stress. It is defined as the normal force, normal component of the atomic bonding forces divided by the area of the surface. Okay, if we process the tangential component, well, F tangential, it is called shear force, divided by the area of the surface. Well, this ratio is called again stress, but it is the shear stress, not normal stress, but shear stress. For shear stress, denoting the shear stress, we use capital T from Greek alphabet, tau, sigma, then tau. The unit of stress, is obvious. Unit of force in SI unit system, Newton, and the unit of area is meter squared. Although unit is newtons per meter squared, on the honor of scientist Pascal, it is written Pascal, capital P, lowercase a. For a strong material such as steel, titanium, stainless steel, these are strong materials. The atomic bonding forces under the action of loading per unit of area may reach to very great values. So instead of writing the stress using lots of zeros, it is more common, it is more practical to write the stress value as the multiple of Pascal, megapascal. Okay. Unit of stress is megapascal in SI unit system if the material is a strong material. In statics, in dynamics, it is the main assumption. Object is under the action of the loads, but its shape remains the same. It is not deformed, even elastically. It is an assumption in statics, suitable assumption in statics and in dynamics. But in mechanics of materials, or say studying on the mechanical properties of the material, for designing an object, to determine its size, to determine its shape, and also studying on metal forming process in the technology, we consider the material, need to consider the material to its real properties, real characteristics. We do not use, say, a non-deformable body assumption. We say that material is a deformable material. In fact, actually, any material is deformed if it is loaded externally by the forces. Okay. Under the action of the loading, the cross-sectional area will be changed. If there is no load, for instance, at the beginning of the work, object is standing on the table and it is not under the action of the externally applied loads. Okay, the only force is the weight of the object. If the loading is almost zero, then the area will be in the original size. If writing the stress value, if we use the unloaded size of the cross section, unloaded size of the area, say that initial area, then the stress is called engineering stress. But if we substitute the area of the selected surface, selected cross section, okay, while it is under the action of the loading, of course, under the action of the load, the area won't be the same of the initial value. It is going to be depending on the loading. it is going to be smaller or some cases greater. If we use the true size of the area, true order of the area under the action of the loading, that is the area of the surface. Not unloaded size of the area, but we substitute the existing area while the body is still under the action of the loading, then the stress is called true stress. True stress. If we substitute the true value of the area, not the initial value but the true value of the area, then correspondingly stress is called not engineering stress but it is called true stress. In solving design problems or in reverse engineering to check whether the existing body can be used under the action of a different loading, we use engineering stress values. But studying on metal forming, studying on the deformations, we use the true stress values. Well, under the action of the load, yes, atomic bonding forces increases to balance the effect of the loads. Okay, so well, at the cross section can define the stress. How about the deformation? If there is a loading, then the body will be deformed. Its shape and also its size will not be the same that of those at the beginning of the process. If we apply a force, then the material will be deformed and the size of the body will be changed. To be able to quantify the size changing, we use a definition. It is said strain. Well, strain. Another thing. If the area in consideration is a finite area, although the atomic bonding forces were not the same at all the points over the surface, their magnitudes are different, not the same. But if we substitute into the expression, stress expression, the total area at the cross section, initial area while engineering stress, true area, true stress. And this is the component of the resultant of the atomic bonding forces. Well, the stress going to be the average stress. But especially at the design stage, we need to know not the average stress, but the stress at any point. To be able to find the stress at a point, well, over the selected surface, we take an infinitesimal small part. Its area is infinitesimally small, and the corresponding bonding force acting to that part of the surface, say that normally directed force, it is infinitesimally small, df normal, and this is df tangential. Then well, since the area is like a point very small in size, then the stress, in that case, it is to be written differential force, infinitesimal small force, and the corresponding area. Then this ratio will give us not the average stress, but the stress at the point. Yes, the average stress may be just at the on the moderate level, but at a certain point the stress may be very great. Well, the generated design equation just saying that the stress at the point must be less than maximum equal to a stress value. Well, for the atomic bonding forces, there is a limit, of course. If this limit is exited, then object will be broken. Because, well, atomic bonding forces thereafter cannot balance the effect of the external loads. Object will be broken. Well, performing some tests under laboratory conditions, well, we determine the limits for the material. For instance, that is the limiting stress value. For being at the safety side, say that, let me say, limiting stress divided by factor of safety for being safety side, and this is called allowable stress, sigma allowable. While the stress at a certain point within the body at any point must be less than the allowable stress. If not, if it is greater than the allowable stress, then over there will be a failure. Object will be broken. Okay. To find the design equation, we consider the worst case, say that stress at any point is equal to maximum, it can be equal to the allowable stress. Okay, using the equality can find the unknown. The unknown may be the diameter of a shaft, thickness of a slab, etc. Okay, we derive the governing design equations using the stress definitions. Say that stress must be less than the allowable stress. Writing such design equations, yes, commonly we use engineering stress. To be able to find the limiting values, we perform some tests and determine the mechanical properties, such limiting values. Before focusing the attention to such a test, it is quite common we say tension test or compression test. Well, turn back to the deformation and then say how it is quantified. How can quantify the deformations? For instance, well, clean the board. Over the surface or within the body, we specified 2 points. Before the loading, the distance between them is equal to that much. And then we apply the forces. Now the body is under the action of loading, and the distance between the points will not be the same because, well, the body is deformed. Okay? If we apply tension force, it is going to be elongated. If we apply pushing forces, compression forces, it will contract. Okay, so the size won't be the same. There will be a deformation. Deformation here is in the linear direction, while the shortest distance between the selected points. Okay, well, this is the initial value of the distance, and that is the value of the distance while the body is under the action of loading. And then, well, definition comes. Well, the initial value of the distance between the selected points, and this is the distance value while the body is under the action of loading. This minus that, divided by the distance between the selected points. If the initial distance is substituted, then, well, this ratio is called strain. Okay, strain. It is denoted using another letter, lowercase e, epsilon. That is the letter. Well, if we select the points being finite distance away, then can find over there the average deformation per unit of length. If we substitute the initial distance, initial value of the distance between the points, then strain similarly will be engineering strain. But if we substitute the distance between the selected points while the body is under the action of the loading, well, initial distance minus the distance under the action of the loading divided by the distance under the action of the loading, then the strain will be the true strain. Okay. Well, in metal forming, studying on metal forming process, we use true stress, true strain. Okay, the strain is dimensionless. Distance divided by distance, it is dimensionless. Okay. Well, to be able to determine the strain deformation at a point, then, well, we select 2 points. These are infinitesimally short distance away. So it is like a point. But if the points are selected very away from each other at a finite distance, then, well, the stress using this formula can be calculated, but it's going to be from here to there the average stress. Average stress is not so valuable. The valuable stress is, the stress at the point, practically. Taking the distance between them infinitesimally small can find the strain at the point, at a point. At the point, what is the stress? At the point, what is the strain? Well, yes, it is true. Between the stress and the strain, there is a relationship. Okay, then, to be able to see the relationship, we perform the tests. Okay, well, see the schematic drawing, tension and or compression test. Well, we have some publications published by standardization associations. Well, in the document it is described. To be able to determine the mechanical properties, limiting values for the material, well, the test specimen is to be in a standard shape, and it is of course to be made of the material. For which material, well, the mechanical properties, limiting values going to be or are to be determined, then yes, manufacture the specimen, test specimen, while using the same material, and then take the specimen and then place it to the test system, test machine. Well, this is the schematically shown test machine. Well, these brownish parts are the gripping facilities of the test machine, and between them this tiny part is our specimen. Well, this machine can apply the load, but in the test the load is uniaxial, axially directed load, longitudinally directed load. Okay, then slowly increase the magnitude of the applied load. Okay, if the test is tension test, then, well, the workpiece specimen will be under the tension. Okay. In compression test, then the force is applied toward the body, not tension but pushing type force. Okay, while the load is slowly increasing, well, the magnitude of the applied force is measured thanks to the existing inspection tools, measurement tools, load cells. Okay, and also the deformation is recorded between the selected points, and all the recorded values, magnitude of the force and the corresponding deformation, these are recorded, okay, within such a box. Well, within the box we have a computer microprocessor. It uses a certain software, convert the measured values to what? To stress, to strain. Okay. And then, stress and the corresponding strain values are plotted. When it is done, then yes, for a ductile material, steel is a ductile material, aluminum very ductile, copper is very well known ductile material. Ductile materials can be deformed in the considerable order. We can see the deformation. It is deformation. The deformation of ductile materials won't be in the infinitesimally small order. Those are deformed, can be deformed in the finite order. Even with naked eye can see the deformation. Okay, and then, that is the famous diagram. Along the horizontal axis, we mark the strain values. Along the vertical axis, stress values. To a certain value of the stress, you know, atomic bonding forces per unit of area, there is such a limit. To this limit, then material behaves like a spring. If the object is loaded, then the body is deformed, but when we remove the loads, then the body can turn back to its original shape. It behaves like a spring, like a perfect elastic spring. By that threshold value, limiting value, yes, material behaves like a spring, as elastic. And to that limiting value, between the stress and the strain, the relationship is linear and stress proportional with strain, or vice versa. To be able to convert the proportionality to equality, we assign a coefficient. That coefficient, such an expression has been introduced for the first time by a scientist, okay, Robert Hooke, as I remember. Have a look at. Yes, Robert Hooke, which time in 1676. Stress is equal to a coefficient times the strain. Okay, it's a line equation, and this equation is valid. This part of the diagram, if the stress is less than this limiting value, yes, the material behaves as an elastic body. If it is loaded, it deforms. If the load is removed, then it can turn back to its original shape, original size. But this limit is exceeded. If the limit is exceeded, increase the load and exceed the limit, then material will plastically deform, permanently deform. This threshold value is called yield limit, and the phenomena is called yielding. Yielding will occur. The material will start to flow like a liquid. It is in solid state, but it can deform. Deformation, if you observe the deformation, it is like the flow of a liquid. So we say that it flows. After the plastic deformation, after a certain value of the loading, then strength of the material increases. when we plot the stress strain diagram, then yes, we see that to be able to increase the strain deformation, well, necessary to increase the applied loading, increase the stress. If we increase the load, applied load, then well, stress also increases. Atomic bonding forces per unit of area increases. But there is a limit. Increase, 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 and then reach to this limiting value. If this limit is exceeded, then well, atomic bonding forces won't be sufficient to balance the externally applied ones. In uniaxial test, the cross section will be drastically smaller, okay, and then atomic bonding forces thereafter cannot balance the external loading and object is broken, fracture occurs. If we substitute the initial size of the area, then we obtain engineering stress, and this drawing corresponds to that stress definition, engineering stress. But instead of substituting the initial size of the area, if we substitute the true size of the area, well, the diagram will be like this. Well, this diagram is to find the true stress, true strain, true stress. Not engineering stress, not engineering strain, but true strain, true stress. Studying on metal forming, yes, we use true stress values. Well, after the yielding, then the deformation will be permanent deformation. Although the load is removed, then object cannot turn back to its initial size, initial shape. We say that it has been deformed. Well, this part of the diagram, yes, the relation between stress and strain is linear, and as it is proposed, introduced by Robert Hooke, stress is equal to proportional with strain, and it is equal to constant times strain. Well, this coefficient is called stiffness of the material, or say it is more common, modulus of elasticity. Modulus of elasticity or Young's modulus. It's an important mechanical characteristic parameter of the material in elastic region. And this expression is the mathematical expression of Hooke's law. Okay, Hooke's law. It's called Hooke's law. Hooke's law. This mathematical expression is valid where in the elastic region. This figure, we see the stress-strain diagram for low carbon steel. This is for aluminum alloy, but that one, you see, well, there is no yielding. Increase the load, have the strain. This part is almost linear, and then, well, without having a considerable plastic deformation, we see that object is broken. This behavior is the behavior of a brittle material. We say that if, well, the deformation is not sensible, cannot be seen with naked eye, and unexpectedly object is broken, then we say that that material is a brittle material. If the material is brittle, then it cannot be used in metal forming, because in metal forming our purpose is to deform the body plastically and change via which the shape. For instance, initial form of the stock is a rectangular prism. After the deformation, it may be just a cylindrical shell. Yes, change it is geometry. But if the material is ductile material, you see here, for instance, low carbon steel is a ductile material. um, see the deformation order from here to there. Strain is a considerable strain, but here for a brittle material the strain is very little. Plastic deformation is very little. For instance, glass is a very brittle material, cannot deform glass at room temperature. Apply the force and glass is broken. Okay. In elastic region, yes, this region, the sigma epsilon relation is linear, and the proportionality constant is the Young modulus. Okay, or stiffness. If the material is in the other region, yielding has occurred and then has been occurred, and the material has been plastically deformed. In plastic region, dear students, the expression derived expressed by Robert Hooke is not valid. In plastic region, yes, by the way, this part just explains what is true stress, true strain. Already talked about it. Well, to be able to find the true strain, take this integral. It is when it is taken, then we find the logarithm of this ratio. Okay, using this logarithm can calculate the true strain value. Okay, and then can plot true stress, true strain diagram. It is similar to the diagram that is plotted using engineering stress and engineering strain. Well, in the region where the material is plastically deformed, corresponds to that region, it is called plastic region. The relationship is similar but not the same. Engineering stress, using engineering stress, can calculate the true stress. How? Well, true stress is equal to engineering stress times 1 plus what? Engineering strain. Lowercase e is engineering strain. Sigma sub e engineering stress. Sigma is true stress. E is engineering strain. Epsilon is the true strain. Okay. Natural logarithm of 1 plus engineering strain gives us the true strain. Okay. Well, in plastic region, to be able to deform the body, continue to the deformation, we need to increase the applied force. Well, increase the stress. From the diagram, we know that it is true. You see, well, to be able to continue to deform the body, okay, well, need to apply greater forces. True stress increases. If need to continue to deform the body, then don't forget it is a must to increase the load, correspondingly have greater stress at the cross section. Since it is increasing, then it is said that strain hardening. If we increase the strain, then the material going to be harder. To be able to deform the material, necessary to apply greater loads. Well, strain hardening is a fact, or it is also called work hardening. Okay. In the plastic region, the expression between the true stress and true strain is in this form. You see, again we have a constant proportionality value. It is called strength coefficient. And well, the power of strain is not 1, it is n. N is different than 1. It is called strain hardening exponent. Strain hardening exponent. Okay, in plastic region, dear students, that is the equation. It joins the strain and stress to each other. Okay. Well, from this table you can see for some materials what is the strength coefficient in megapascal, what is the strain hardening exponent. For instance, for low carbon steel, strength coefficient is 500 megapascal, strain hardening exponent is 0.25. Well, if the material is the one, well, it cannot be deformed. Well, it behaves like a spring. Between the strain and stress, the relation is linear. Then it is called perfectly elastic material. After the yielding, although the stress is not increasing the same, but material continue to flow, continue to change its shape, then we say that it is perfectly plastic. Perfectly plastic. Well, in the jargon, since after yielding material like a fluid flows, deforms, with naked eye, even with naked eye, deformation can be seen. It is similar to the flow of a liquid. So in the analogy it is said this curve is the flow curve. Okay, flow curve. If someone says flow curve, then this means it is the equation well written for finding the stress using strain or vice versa. Stress, true stress is equal to strength coefficient times the n power of true strain. Well, at room temperature, if the material energy level of the material is at the room temperature level, then the stress strain diagram will be like this. Well, for which material? For ductile material. Elastic behavior and then plastic deformation. Okay. If the stress strain diagram for the material is like this, then in short say that that material cannot be used in metal forming because it is very brittle under the action of further loading. It is broken. Well, this material can be used. First it behaves as elastic, and then, well, it can easily flow, it can easily be deformed. But unfortunately for steel, well, the stress cannot be constant, cannot remain the same during the deformation. It starts to increase. We say strain hardening. While we are straining, while we are deforming the body, it is going to be more strong. To be able to continue to deform the body, well, need to increase the external loads, need to have greater stress values. Okay. Perfectly elastic. These materials are not good for forming. Elastic and perfectly plastic. Yeah, yes, figure B, elastic and then perfectly plastic. If it is perfectly plastic, then, well, the strength coefficient will be equal to yield limit, and the power of through strain will be equal to 0. For instance, lead behaves almost, well, elastic and perfectly plastic material. Most ductile metals, steel, for instance, behave this way. What? Elastic and then strain hardening phenomena in plastic region. If the material is at room temperature, we say cold working, then the behavior of ductile materials corresponds to this diagram. Elastic and then plastic behavior, but in plastic region, stress is to increase to have the strain in continuation. Yes, dear students, metal forming includes a large group of manufacturing processes. Well, see this classification: metal forming, bulk deformation, sheet metal working. Bulk deformation process, yes, the stock, the initial form of the body is the one, its thickness is comparable with the other size. But relative to the surface area, if the thickness is very little, then we say sheet metal. Especially the thickness of a rectangular prismatic body, it is made of a certain metal, is less than 12 millimeters, then it is called sheet metal. In English, sheet metal; in Turkish, sac levha. If the thickness is greater than 12, then it is called slab. Bulk deformation or sheet metal deformation, ductility is quite important. To be successfully formed, a metal must possess certain properties. Desirable properties include low yield strength, high ductility. If the yield limit is small, but the deformation willingness, ductility is high, then this material is a quite good material to use in metal forming technology. Ductility is a measure of a material's ability to deform plastically, permanently, before fracture. Okay. Ductility, this is important, is increased and yield strength is reduced when work temperature is raised. If we heat the material up within a furnace, then it is going to be more ductile. It can much more easily be deformed plastically. It is yield limit decreases, and it can easily flow. It is going to be more ductile. That is the reason why in metal forming it is quite common to increase the temperature of the material. Before the deformation stage, to be able to decrease the magnitude of the forces these are to apply to deform the body, we put the object stock into a furnace, we heat it up. At a higher temperature, much more easily can shape the object. But if the temperature is almost the room temperature, then the deformation process is called cold working. If the temperature of the material is at intermediate order, then it is called warm working. If it is greater than a certain threshold, it is called hot working. Strain rate and friction are additional factors that affect performance of metal forming. Bulk deformation, well, the processes to shape the stock are rolling process, forging process, extrusion process, wire and bar drawing process. In sheet metal work, the common processes to shape the material are bending process, deep drawing process, and if necessary to cut, then shearing process. It is a cutting process, and some other processes, miscellaneous processes. In bulk deformation processes are generally characterized by significant deformation and massive shape changes. Starting work shape for these processes include cylindrical billets or rectangular prisms. The common shape of stock, the initial shape of the body is cylindrical or rectangular prism. Well, one of the bulk deformation process is rolling. And rolling process, we have rolling machine. Well, of course, we have the rollers only here. It is a machine, it has a motor, it has a say driving mechanism, it has an amplificator, and at the end, at the actuator part, what we have cylinders. Well, decreasing the distance between the cylinders, well, can increase the force. Okay, these are applied by the rollers onto what? Onto the stock. Well, this part, well, the body is called stock, and at the other part it is the product. Yeah, yes. While the rollers rotating, thanks to the friction forces, then the stock is taken in this direction, and the forces those are applied by the rollers can plastically deform the material and then output the product. Well, if over the surface of the rollers, well, there is no cavity, there is no rim, then well, the product will be again in the rectangular cross section. Stock is a rectangular prism, and the output is a rectangular prism, but the only thing it is different, the thickness going to be smaller. To decrease the thickness, yes, apply rolling process, for instance. But if the rim of the cylinder, say that see the cylinder laterally, okay, this is the longitudinal axis of the roller, and for instance here we have what? We have such a, say, space, circular. Okay, using such a say roller, well, of course it is all around, apply the deformation process, then the shape of the product can take the shape of this space. It is going to be not rectangular cross section, but it's going to be a circular cross section. If in the rim we have L-shaped cavity, then well, the product will be L-shaped prism. Okay, well, later, this is just the chapter about the ABC of metal forming, some definitions, and a review part on the mechanical properties of material, and strain stress definitions, and the relationship between stress and strain. While the details about rolling process, the subject of another chapter. Okay. Well, similarly, The other deformation process is forging. Again, we have a huge press. Well, that press is to apply the deformation force. Well, similar to casting, we have dies, and the dies have the negative of the shape of the product. We put the stock between the dies at the beginning and then apply the deformation force. Well, the material of the body first elastically behaves and then yielding occurs. After the yielding, it is going to be permanently deformed. Whatever the geometry of the cavity of the die is, then the shape of the product going to be almost the same. That process is called forging. In forging, a workpiece is compressed between two opposing dies so that the die shapes are imparted to the work. Forging is traditionally a hot working process. To be able to deform the body drastically, a very great forces are needed. If we deform the body in room temperature, at room temperature, well, the order of the forces will be few hundred tons. Even we cannot find such a press machine to apply such a very great, extremely great force. To be able to use a moderate size press and to be able to decrease the magnitude of the force to apply, yes, the thing to do is that heat the material, okay, while the material is hot, then shape it. Hot working, okay, to be able to decrease the size of pressure, size of the force, size of the press machine. Yes, the solution is that increase the ductility of the material via heating the material before the deformation stage within a furnace. In extrusion process, similar to extrude, but the material is not liquid, it is solid. While applying a very great force at this end, we have an orifice here, okay, we have a die and it has an orifice there. While applying such a great force using the ram of the press machine, we force the material to flow via deforming, of course. We force the material such that it deforms plastically. It is like the flow of a liquid. Yes, it can move in this direction and takes the size of the orifice, almost the size of the orifice. Okay, swell ratio is very small since the material is not liquid, not plastic, but a strong material. Swell ratio is almost 1. Not 1, sorry. Almost 1. So, the size of the product is almost equal to the size of the orifice or the die. In extrusion, the material is pushed, compressed, and it is forced to flow across the orifice. But in the other method, these are bulk deformation methods, it is drawing. Instead of pushing the stock toward the die, we pull the stock at the other side. It is drawn. The method is called drawing. In this forming process, the diameter of a round wire or a bar is reduced by pulling it through a die opening. Okay. And sheet metal working, yes, the thickness is considerably smaller than the width and the depth of the prism. It is called sheet metal, and the shaping process is called sheet metal work. It is a press work actually. Okay. Well, as it is illustrated in bending, we have a die, and applying the deformation force, we can bend the sheet and change its geometry. Uh, the other process is called drawing, but to be able to distinguish or highlight the difference, it is not such a drawing, but it is different. Well, to highlight that it is a different drawing process, it is said deep drawing or cup drawing. And deep drawing, well, first sheet metal is put onto the table. We have the die over the table of the press, and die has the negative of the geometry of the product. While we're gripping the ends of the sheet metal, apply the deformation force using the ram of the punch of the press. Okay, depending on the geometry of the end of the punch and the geometry of the cavity, it is plastically deformed while these ends are still kept at their places. They are gripped. Well, we apply the deformation force and plastically deform the material. This technique is called deep drawing. Process is deep drawing process. If it is necessary to cut the material, yes, we use shearing machine, shear cut, like scissors, and then while applying again the force, necessary force, we cut the material. It is the shearing process. And then, well, this part, yes, the relationship between the stress and the strain, yes, is expressed as equal to stress is equal to strength coefficient times true strain power n. Well, that stress is also called flow stress in the analogy because during the deformation, well, it is like a fluid, like a liquid, it moves quickly from one side to the other side. The flow curve describes the stress-strain relationship in the region in which metal forming takes place. Flow stress is defined as the instantaneous value of stress required to continue deforming the material to keep the material flowing. It is the yield strength of the metal as a function of strain, which can be expressed. Yes, this is the yield limit. What else? In certain forging operations, the instantaneous force during compression can be determined from the flow stress value. Flow stress value. Well, flow stress means yield limit. Okay, yield limit. Yes. As the billet, for instance, this is a billet cylinder, is reduced in cross section to pass through the extrusion die opening, the metal gradually strain, hardens to reach a maximum value. Rather than determine a sequence of instantaneous stress strain values during the reduction, which would be not only difficult but also of limited interest. It is more useful to analyze the process based on the average flow stress during deformation. Okay. Deformation, instantaneous deformation, but say since the cross section is gradually changing, it is a little bit difficult to find the instantaneous deformation and the stress. It is more common and more useful to analyze the process using average flow stress during deformation. Flow stress. What is flow stress? One more time say. The flow curve, this is called flow curve, describes the stress-strain relationship in the region in which metal forming takes place. It indicates the flow stress of the metal, the strength property that determines force and power required to accomplish a particular forming operation. Well, after finding the flow stress, then can calculate the power of the motor or the press machine, for instance. Later gonna practice on such things, such examples. Yes, this is the yield strength of the metal as a function of strain. Flow stress. Flow stress, it is said flow stress, it is the yield limit actually. Okay. The flow curve, this sentence is important. The flow curve is generally valid as a relationship, this is the flow curve, that defines a metal's plastic behavior in cold working. Well, this flow curve is more applicable or valid in cold working. If the material is not very hot but at almost room temperature, it is said cold working, then this equation is valid. Average flow stress, how it can be calculated? The average flow stress, well, yield limit, final stress value, average. The average flow stress is determined by integrating the flow curve equation between the initial and the final strain values. Initial strain, final strain. The equation average flow stress, while the stress value in the plastic region is called flow stress. The initial value is the yield limit, final value is the fracture limit. It is broken after this limit is exited. So the average flow stress is such a stress value. How it is calculated? Average flow stress, well, coefficient through strain, power and power of through strain divided by 1 plus the power of the strain. Okay, this one. Yeah, yes, here K is what? K is strength coefficient, capital K. Temperature in metal forming is important. Increasing the temperature, we can decrease the necessary stress value. We can decrease the magnitude of the force that is to apply for the deformation. Well, 3 temperature ranges are defined: cold metal forming, warm metal forming, hot metal forming. Cold working, warm working, hot working. What are the threshold values? Cold working, if the temperature of the material is the room temperature, at the room temperature, 20 is the standard temperature, 20, 25, 30, okay? Then yes, we say that cold working. Advantages of cold working, well, greater dimensional accuracy can be satisfied, obtained, better surface quality, higher strength and hardness of the part due to strain hardening. Grain flow during deformation provides the opportunity for desirable directional properties to be obtained. Since no need to heat, well, can have the manufacturing cost at a smaller level. Hot working, well, heating requires thermal energy, burning a certain fluid or using electricity we can increase the temperature, but such a stage is not free of charge. It's an expensive stage. So, well, cold working is cheaper. But the disadvantage, well, in room temperature, cold working, the material will be more strong. So, well, a greater forces are to apply. Higher forces and correspondingly greater power of the driving unit are required. Well, care must be taken to ensure that the surfaces of the starting workpiece are free of scale and dirt. Yes, if we have oxides over the surface, then well, deformation cannot be in the correct order. Ductility and strain hardening of the work metal. Well, sorry, what is going on? Well, I received a calling, unfortunately. Well, turn back to here. Sorry for this. In warm working, well, increase the temperature but not too much. The threshold value is that if the temperature of the material is the 30% of the melting temperature, here this is important, the temperature unit is not Celsius, it is Kelvin, absolute temperature, 30% of the absolute value of the melting temperature is the limit. If the temperature of the material is less than this limit, then it is called warm working. Well, that is the temperature, okay, above the room temperature but below the recrystallization temperature. Advantages of cold working, over cold working. Advantages of warm working: lower forces and power, more intricate work geometry is possible, need for annealing may be reduced or eliminated. What is annealing? Annealing, heating material and then allowing to cool slowly in order to remove internal stresses and make it easier to work. For instance, copper tubes must be annealed after bending, or otherwise they will be brittle. In hot working, the temperature of the material is set to such a level, 50% of melting temperature. Well, in practice, hot working is usually carried out at temperatures somewhat above 0.5 times the melting temperature. If the material is very hot, then well, can much more quickly react with the surrounding air, atmospheric air, and over the surface, unfortunately, we have scale. Scale means a layer of oxides. Okay, a scale on the work surface is accelerated at higher temperature. Well, the advantage of hot working is obvious. The material is very ductile, so smaller forces going to be sufficient to deform the material. Accordingly, hot working temperatures are usually maintained within the range 0.5 times the melting temperature to 75% of the melting temperature. Okay. Advantages are written here, disadvantages there. And then, dear students, well, the last part is about strain rate sensitivity. Well, if the strain speed, deformation speed increases, then correspondingly the stress value going to be greater. If we slowly deform the body, then smaller forces may be sufficient, but if we increase the speed of deformation, it is going to be necessary to apply greater forces. Theoretically, a metal in hot working behaves like a perfectly plastic material with strain hardening exponent 0. That the material should continue to flow under the same level of flow stress. Once that stress level is reached, however, there is an additional phenomenon that characterizes the behavior of the metals during deformation, especially at the elevated temperatures of hot working. That phenomenon is called strain rate sensitivity. The rate at which the metal is strained in a forming process is directly related to the speed of deformation. Okay, deformation V. For instance, apply the force in forging process with a speed. If we increase the deformation speed, yes, then the material will behave being more sensitive to this attempt and will react to this quick deformation. Given the deformation speed, strain rate is defined. How? Yeah, strain dot, it is the rate. What is that? Deformation speed divided by, strain rate will change as, h is instantaneous height of the workpiece. Deformation speed divided by the instantaneous height thickness of the workpiece. This ratio is called strain rate. Strain rate. Okay. It is observed that the flow stress of a material is a function of temperature. At the temperatures of hot working, flow stress depends on the strain rate. The effect of strain rate on strength properties is known as strain rate sensitivity. You see, this figure, if we increase the strain rate, then flow stress increases. This means, to be able to decrease the magnitude of the deformation forces, these are needed to deform the material, decrease the deformation speed. Slowly deform it, not very quickly. If you quickly attempt to deform it, then it is going to be necessary to have greater stress values. Material will be sensitive to strain rate sensitivity. Yes. We have again an equation. Flow stress is equal to a constant times m power of the strain rate. Pay attention to the dot. It is not strain but strain rate. What is strain rate? Speed of the deformation speed divided by instantaneous height or instantaneous thickness. Flow stress, strain rate, flow stress decreases with the increasing temperature, but you see the slope of the curve increases with the increasing temperature. Yes, there is a table to see the coefficient of friction, strain rate sensitivity, and temperature ranges. In hot working, press work between the surface of the object and the surface of the die, there will be very great forces, friction forces. to be able to decrease the order of the power consumption, well, it is a must to lubricate the contact surfaces. In hot working, lubricant, commonly used lubricant is glass, liquid glass. Using glass in liquid phase, we decrease the friction. We lubricate the contacting surfaces. Yes. Cold working, friction coefficient. Hot working, you see friction coefficient is greater. To be able to decrease the effect of friction, yes, lubrication is important. The commonly used lubricants in hot working: mineral oils, graphite, glass. Glass is more common. In cold working, lubricate the contact surface to decrease the magnitude of the force to apply, using mineral oils, fats, fatty oils, water-based emulsions, soaps, and other coatings. Okay, dear students, that is the end of my presentation. It became a long presentation, as usual. Okay then, ending the recording. That's all. See you later. Bye bye.